So we look through the substitution reactions. So let's take a look at our eliminations. If we look at an E1 elimination, so first and foremost, what does the 1 mean to you?
There's actually 2 steps that are going to happen.
Okay, so we can go with
Spread out.
2 steps. I'm actually going to put that a little bit lower on this. Okay, which isn't a bad thing to remember. The problem that I've always got with that is you've got SN1, SN2, E1, E2, and you got lots of 1s and 2s, and if you now start throwing, oh, well, 2 is 2 steps, so that means SN2 and E2, except it doesn't. Okay, it means the 1 isn't in reference to the number of steps. So that's my problem with that. If you can keep it straight, by all means, go ahead and do that. Okay, that 1 means carbocation. And if you remember that it means carbocation, that actually tells you that you need 2 steps. Because if it did the elimination in 1 step, you wouldn't form a carbocation. Okay? So if you know carbocation, that tells you 2 steps. And if you know carbocation, that will also tell you other pieces of the puzzle, okay, that 2 steps doesn't necessarily tell you. Okay? So if we're now looking at our initial structure, okay, we would start with a substrate that has a leaving group on it. Because we're forming the carbocation, we know the leaving group must leave first. That's going to have our leaving group with a pair of electrons, maybe charged, maybe not, and then we'd have the carbocation. Okay. This should be familiar. It should match exactly with the SN1. That's because it does match exactly with the SN1. Okay. Now what happens? Well, if we're going to do an elimination, we have to make a pi bond. To make a pi bond, we need an extra line. That extra line means we need more electrons, and currently our structure is missing electrons. Because we cannot take electrons from an atom and just throw them through space and give them to another atom or another place. We have to take electrons from within the molecule. Where are we going to find them? We're going to find them from a hydrogen located in the beta space to our leaving group left. So we've got alpha and beta. Most leaving group positions have 2 beta spaces. Okay, so we could remove potentially 2 different hydrogens, resulting in 2 different products. Okay, and if you're looking at this and be like, well, doesn't that look like 3 products? We'll cover that in a second. Let's address kind of that purple hydrogen, which should lead us to our purple product versus the blue hydrogen. Both of those stabilize the carbocation, but the difference comes in to play with the final product. The products are different in energy. How is the purple product different in energy than the blue product?
More stable.
Okay, perfectly accept. Purple product is lower in energy. Yes. Why?
Chains.
What's that?
Chains.
What do you mean chains? I don't understand. Okay. Because I could draw the blue product like that. That's equally valid for the blue product. So if you're telling me because I've got a chain, I would argue the blue product also has a chain, so I don't understand that.
No, I mean trains, not cis.
Is the blue one trans or cis?
Cis.
It does not have cis-trans isomerism. So we go back to our unit 1 when we talked about cis-trans isomerism. We cut our double bond in half and we compare the 2 pieces of the half. Can I tell a difference between hydrogen and hydrogen? No, which means I can't star either one of those, which means there is no cis-trans isomerism for the blue structure. Is cis-trans isomerism something that's going to become important? Yes, it will. But we have to cross this bridge first. So cis-trans is not relevant to us. Why is the purple one more stable than the blue one?
The methyl group, the opposite sign, far away.
You're referencing cis-trans again.
Double bond on the purple can shift either left or right.
Resonance.
Shift, okay, shift sounds an awful lot like resonance. Can we do resonance? Nope, no resonance. And black at the bottom. Which carbocation is more stable?
The next
The left one. Why?
3 carbon.
3 carbons connected to it. It is more substituted. Which product is more stable, the purple or the blue? Purple, because it is more substituted. The exact same reasoning falls into play. Okay? This was something we talked about when we talked about our alkenes and our alkene stabilities. Okay? We have an alkene functional group here. The more substituted the alkene, the more stable it is. Okay? So between the two choices, purple versus blue, we want the one that produces the most stable product. That's going to be what drives that last step. Since the blue one produces a less stable product, it does not make sense for me to remove the blue hydrogen, and instead I target the purple hydrogen. Yeah, we're just going to leave all those marked up there. Which means I should get rid of the blue structure. Annie brought up a good point, though. Isn't it possible that I do the elimination in such a way that I get the cis alkene? Yes, it is possible. Is that more or less likely than forming the trans? And if you're trying to search for that explanation, it's the same explanation that we just walked through. Should I get the purple product or the blue product? Purple, because it's more stable. Cis versus trans, which one should I get? Purple or black? Purple, because it's more stable. Okay? Knowing the stability of our alkenes dictates what answers we get when we run our E1 eliminations. Okay? We're already forming a higher energy structure by making a pi bond, so we want to form the most stable pi bond possible. Okay? That observation was named after the person who theorized this, and that's Zaitsev. So we get Zaitsev's rule. We form, technically, you remove the hydrogen. No, I'm thinking Markovnikov. No, you remove the hydrogen from the carbon that has the fewest hydrogens. Okay? And if that sounds confusing to you, I completely agree. I think it's a dumb way to phrase it. Okay? But that's all he had access to. He didn't know what an electron was. Okay? This rule was defined in, I think, 1876 is when he first coined it. The discovery of an electron, or direct evidence of an electron, is 1898. 20 years later. Okay, so it's kind of cool that someone could go through and say, this is what I think is going to happen when we do these reactions. I'm going to form the most stable double bond. We didn't say that. He said where he was removing a hydrogen from. Okay, that's pretty powerful, and that's why it gets named. Okay, the historical kind of artifact behind them. So when we go through and now do our elimination reactions, once we understand what's happening within the mechanism, we can now start to make evaluations based off of our substrate. Okay? Well, the substrate could change. That's that blue thing at the beginning. Okay? That substrate could be where we have 2 carbons and a hydrogen. Okay? Around that structure, in which case we get minimally a doubly substituted alkene, or sorry, a singly substituted. Okay? What if we added another carbon there? Would that increase the substitution? Yeah. Okay? So what I can do is consider the chemistry of the substrate at that alpha position, and I can say, well, what chemistry do I want? Well, I want the most substituted double bond, which means the substrate should be the most substituted possible substrate, which means I would favor tertiary over secondary over primary. Zeroary wouldn't come into play. Why would the zeroary be ignored? What did we say zeroary meant?
Cannot make carbon.
There were no carbons connected to it, meaning these were all hydrogens. Do you have a beta position? No. And with no beta position, you can't do the elimination. So the zeroary doesn't come into play when talking about the E or our eliminations altogether. Okay. We also have the leaving group, unfortunately overlaid there, so I'll rewrite the substrate in a second. Okay. Do I need a leaving group? Yeah. I can't form a carbocation if I don't have a leaving group. Okay, so what would be a characteristic of the leaving group? Well, it would be the exact same characteristics of the leaving groups that we saw for substitution. It needs to be an element that would take electrons away from carbon. So what things would take electrons away from carbon?
Iodide.
Iodide. Cool. Bromide, chloride, what do they all have in common?
They're large and more stable negative.
Okay. These are large and able to stabilize the negative. Okay, stabilize those electrons once they leave the structure. Okay, what else would be a decent property of something that would take electrons away that sort of iodide, bromide, and chloride all have in common?
Nucleophile. Or electrophile.
A weak base.
We can talk about weak bases, but since we aren't good at ranking weak bases, I would argue using the definition of a weak base is a horrible idea, and I hate that it's taught that way. It's not wrong, but if you struggle to identify what a weak base is, saying a weak base is pretty stupid. They had to take the electrons away from carbon. Would hydrogen do a good job of taking electrons away from carbon?
Oh, they're the forces and bonds.
We could talk about the bonds. What kind of bond would you expect?
Negativity.
You're typically looking at highly electronegative elements. Okay? So electronegative En, or you can use the chi. Okay? Those would be common characteristics. Iodide, bromide, and chloride are all pretty electronegative. Okay? Why do we not list oxygen or nitrogen? Why is OH minus not a particularly good leaving group?
Because it's a better acid.
It's negatively charged, so it's not a very good acid.
In terms of like delegating or accepting the hydrogen.
Why is that relevant?
Because that's what we see with acid and base reactions.
Is that an acid-base reaction?
No. So it's just
So why is it relevant?
because you're asking why we didn't list oxygen there?
Yeah, why do we typically not see negative oxygen there?
Because it's an elimination reaction? Because oxygen is...
Why did we list iodide, bromide, and chloride?
Because they're large and they stabilize
They were large, and because they were large, what did they do?
Stabilize the negative.
Stabilize the negative.
Oxygen.
Why do we not look at OH minus?
It's not as large.
It's not as large, and more importantly,
It doesn't stabilize.
it doesn't stabilize the negative. Why not? What do we know about hydroxide?
That same hydrogen.
It's a strong base.
Strong base.
We know it is reactive. If it's reactive, it ain't stable. Stable means it does not react. That's the whole point of stability. Okay? So that's where that weak base kind of theory comes into play. Okay? But there's other ways that you could change the reactivity so that you could have oxygen act as a leaving group. We want oxygen to stay, or we want our leaving group to stabilize the electrons as it leaves, right? So let's go back up to our substrate where it says leaving group. You know what? Mike said oxygen is a bad leaving group. Let's go ahead and do it. OH is a bad leaving group. How could it possibly leave? How could it possibly take those electrons away? Because if it does that, what happens?
Exceeds its octet.
Cool, it exceeds its octet. Let's take a look at the Lewis drawing. Does that exceed its octet?
Yes.
I mean, it makes it neutral.
Oh, no.
What does octet mean? 8 electrons. How many electrons are around that oxygen? 8. Did it exceed its octet?
No.
No. It's not stable because the oxygen is small. Right? Can't stabilize the electrons, but it is electronegative, so it is willing to take the electrons, but it's not stable on its own. How could I modify it so that it would be stable?
Hydrogen.
What happens if I take one of those lone pairs and I say had a hydrogen on it? Would it be negative anymore?
No.
No, it would not. That's why it would be stable. Okay, I've stabilized the negative. It's not a negative. I've stabilized the electrons by ensuring that when it leaves as neutral. Okay, I can't put the hydrogen onto the negative oxygen because the negative oxygen can't exist. We just said it doesn't happen. So where does that hydrogen need to appear? Or where does it also need to appear, I should say?
Acids.
Yeah, it needs to appear in a strong acid. Where does it need to appear in our reaction? Because you said if I put a hydrogen on it, it's neutral. Great. Where does that hydrogen need to appear? Because if I said another way, I can't go through and say this is negative and no, now I put on a hydrogen and get OH and be like it's neutral. Because that assumes I made negative oxygen. I can't make negative oxygen. So where should the hydrogen first appear?
In the solvent.
And we can reference the solvent, but go shorter distances. Where must that hydrogen appear? You want it connected to the oxygen, right? You want that bond connected to the oxygen. But we can't connect it out here. This isn't allowed. So where should I connect that hydrogen?
Just on the molecule already.
How about I connect it back here? What charge would the oxygen then be?
Positive.
It would be positively charged. Does oxygen want to be positive? No, so what does it do?
It'll leave.
It leaves. Oh my goodness, there it is. So now it's not leaving as a negative. I still have oxygen as a leaving group, but I've never formed hydroxide. That's fantastic. Okay. The next question, which you were all trying to jump to and answer first, is how do I get that hydrogen on the structure? Well, that's one step further back. There's my alcohol. How can I get that hydrogen on there? What does my alcohol act as? Let's spin this. I think I can spin this way. What is this guy acting as to look like this guy? What changed to its structure?
A base.
It acts as a base because it accepted a hydrogen, which means what should I react it with?
An acid.
What acid would I like to react it with?
Strong.
A strong acid. There we go. So we could say add HCl. What happens? The electrons from our oxygen go here, go here. We now have a great leaving group. Now the leaving group can leave. Ta-da, now I can continue the rest of the reaction. So this elimination can be preceded by an acid-base reaction to activate the leaving group. So instead of going through and saying, oh, this is a bad leaving group, it never leaves, how can you make it a better leaving group? Look at what it needs to do. It needs to stabilize charge. And if we think back to how we've talked about everything, that's literally how we've talked about everything. How do we stabilize charge? What do you have to do? And think slow steps. Well, I got to do this. Okay. Well, now that I've done that, how can I do that? Well, let's go back one step. Back one step. And what I'm seeing a lot of people do is you're trying to go back 6 steps. Okay? You're trying to play chess with a grandmaster and trying to plan out 6 steps. They can see 6 steps ahead. You can't. Stop it. Play 1 step. Eventually, you can plan out multiple steps. You aren't there yet. Plan 1 step at a time. So, leaving group. Large electronegativity, right? The primary driver behind it is I need to stabilize that negative charge. Weak bases, by definition, stabilize that negative charge. So how about we just say stabilize the negative charge instead of talking about bringing in another word to describe that system? Okay? What else do we evaluate when we look at our overall reaction? Okay? Well, in this system, we do need a base. Pull all that stuff back out. Okay? I need a base. Why do I need a base? What's happening in that last step? We'll draw the trans one. Emphasize that one. What happened in that last step?
We donated hydrogen,
What things donate hydrogens?
acids,
Acid. So our molecule acts as an acid. What should I react it with to help that reaction along?
a base.
That's why we talk about bases when we look at eliminations. Okay? Do we need a base to break bonds?
Not necessarily.
No. Okay? I can put a log of wood into a fireplace. I'm not adding bases to that. And yet I'm doing a chemical reaction. Okay? How is that chemical reaction being initiated?
Heat.
Heat. Okay? So do I need heat or a base to do this reaction? It's a harder question. And by this reaction, I mean this last step, or step 2.
With what you have on the board right now, you would need
Sure.
base because you have an acid.
Or I could add heat. So what I'm asking is, do I need a base or a heat to do that? It's kind of a hard question. So let's shift to a potentially easier one. Let's look at the previous step, step 1. Do I need a base or heat to do that first step? I know there's words written there, but don't worry about the words, worry about the question. Do I need base or heat to cause the leaving group to break off?
No,
No. Why not?
because the leaving group is going to want to leave by itself.
Why?
Because it's positive right there.
Isn't necessarily positive. If we made it the oxygen, yeah, it's positive.
Because it has a high electron negativity, so it's gonna wanna pull.
Ooh, I love that answer. There's a high electronegativity in that bond, causing the leaving group wanting to take the electrons. What kind of bond is that?
Sigma.
True, fair, answer. Try again. Another bond classification.
Like, polar covalent?
It's not covalent, it's
Polar covalent?
polar covalent, because we have a large difference in electronegativity. Now look at step 2. What bond are we trying to break?
The hydrogen?
The hydrogen to what? Carbon. Would I expect that bond to break on its own?
No,
Why not?
because it's non-polar covalent.
It's a non-polar covalent bond. So to get that bond to break, I have to add something to cause it to break. Which means in that second step, do I need a base or heat? Yes. Okay? The definition of heat can be very shaky, right? Which is why we don't go into that and we just say heat or a delta symbol. Okay? And we leave it at that for the sake of this class. But to get that bond to break, I need a base or heat. Okay? Because something has to pick up that hydrogen. What is the base? What is the characteristic of the base? What must it have?
Electrons.
Is that it? That's a nasty question. I apologize for that. Do all structures have electrons?
Not a hydrogen?
A hydrogen atom technically does, but a hydrogen ion, you're right, does not. I would argue that's not a molecule, though. You're just looking at a single atom. Do all structures have electrons?
Yes.
Yes. So can you nuance your electrons a little bit better?
It has to have a negative charge because it's going to want to pull back.
And that's what I was fishing for. Does it have to be negative?
No.
No, it just has to be available electrons. What are available electrons?
Lone pair.
Lone pair is our biggest signifier for a base. Okay. Technically, our pi bond can act as a base as well, but we'll talk about that in more detail later. We need available high energy electrons. That's talking about lone pairs and pi bonds. Okay. It does not have to be negatively charged. If it is negatively charged, it is typically a stronger base because it's now charged. So that goes to the charge size, electronegativity, all that fun stuff. Okay? So we're looking at caveats behind each of these classifications by drilling into the exact minuscule detail that is necessary for each. Okay? When we look at the E1, how important is the base? So we've got 2 steps in the elimination. Which of those steps do you think is the most challenging to do? That's a really hard question. It's one that becomes easier if we look at an energy diagram. We've got our reactant. The carbocation is higher in energy than our reactant, so we should go up. And then our pi bond is higher in energy than our reactant, so we'll go down here. Which of those steps is going to be the hardest step to complete?
The one that has the more energy, or that requires more energy.
What energy are you talking about?
Activation energy.
There's the activation energy for the first step. Where's the activation energy for the second step? It's that tiny space. It's not from where the reactant is because it's a new reaction step. It's from the carbocation. That one, even though we're breaking a harder to break bond, right, is going to be a smaller activation barrier because we're looking at a charged structure versus a neutral structure. So what does that mean? The first step is the only step we really care about. Is the base involved in the first step? No. Which means when we think about properties of the base, I don't need it to be strong. I just need it to have a pair of electrons. That's it. So I'm looking for not strong bases. What else would I need to worry about? Well, I could look at the solvent. Okay. The solvent in elimination reactions is very misleading, so I would caution any kind of use of looking at solvents for eliminations. Okay. But we can get away with it, particularly for the E1, for one major reason. When it's an E1, what do we need to remember as our first and foremost aspect? Carbocation. If we know we're forming a carbocation, we must form two steps. Okay? So, carbocation. Can a solvent stabilize a carbocation? What are the different solvents? So we could start to get real specific. Oh, there's alcohols that are solvents. Yeah, you could do that. I would argue that that's now getting really into the weeds. It would be nice if we had broader definition categories that we could use. Like protic, polar aprotic, and nonpolar. And if we have those categories at hand, kind of like why we talked about them initially, so that we had those classifications, we could use them, we could now say, what do each of them bring in that could affect the carbocation? Well, would a nonpolar solvent affect a carbocation? Why not? I'm talking about the interaction between a nonpolar substance and the carbocation. Why would I expect the nonpolar substance to not interact very much? What forces are generated by a nonpolar solvent? London dispersion. Why do we call them London and not name them after the interaction itself? Because we're naming them after a person. Why do we have to name them after a person? Because we thought they were irrelevant until some smart ass came along and was like, nope, they're not irrelevant, they're important, you got to think about it. And so now we hat tip to that person for having identified and forced us to look at them. Non-polar covalent bonds are so strong, they have very weak interactions, which is why they all go up into the gas phase very, very swiftly. And if they have weak interactions, is it going to interact or affect a carbocation? No, because it doesn't interact. That's the definition. What happens if we make it polar aprotic? What do we want to stabilize that positive? A negative. What does the polar aprotic produce? Where's that negative? On the oxygen, of course. Why? Why does that oxygen become partially negative? There's two very good answers for this particular one. Oxygen is more electronegative than the carbon. You mean the oxygen is connected to the carbon via a polar covalent bond? Yes, that's why it's a polar solvent. That's why it's picking up that partial negative charge. What's the other reason? Resonance. Resonance actually shows a negative charge building on the oxygen. Yes, both of those things would suggest that oxygen can stabilize that negative or that positive charge very well. What's our last option? How about a polar protic solvent? Okay, we could talk about hydrogen bonding, true. Do we care about hydrogen bonding necessarily? What are we trying to stabilize the positive with? A negative. Are the hydrogens negative? No. So saying hydrogen bonding is a bit misleading. Yes, it has hydrogen bonding, but that's not the part that I care about. What's the part I care about? The partial negative on the oxygen, the partial negative on the oxygen in the polar protic. Those are what can stabilize the positive. Which of those would have a larger positive? Or sorry, larger negative? The protic one, yeah, cool. Why would the protic one? So we could use that. And so you're saying that this one in our protic has some bulk behind it that could potentially get in the way. That's possible. Why else would the, and that isn't really changing the negative size of the negative oxygen. That's just saying the negative oxygen is hindered by something else. Why is the negative oxygen in our protic typically more negative than in the aprotic? What is the bond between the oxygen and the hydrogen? It's a polar covalent bond. What is it between the oxygen and the carbon? Polar covalent. Are they the same polar covalent, or are they a little different? The difference in electronegativity between the hydrogen and the oxygen is significantly larger than it is between the oxygen and the carbon. Therefore, meaning the oxygen in a protic environment is more negative and therefore can stabilize the positive better. So what does that mean for us as far as the solvent goes? We want protic solvents. And how did we figure that out? We remembered that E1 is carbocation, and we go through the definitions of all of those individual pieces, and we apply that back to the core fundamental piece behind it. Everything stacks. We then encounter extra fun terms, regiochemistry, okay, and potential benefits. At this point, I want to just delete everything so we can cover those words. Officially, we've already talked about those. Can I delete everything that's up there? Hit us to our summary. Okay. Our regiochemistry. The regiochemistry is saying where does the chemistry happen or where does it form? So when we talk about our regiochemistry, we're talking about forming the most substituted double bond. That's our primary aspect for our regiochemistry. We can do a little bit, I think officially it starts to move into the stereochemistry realm when we talk about trans. Okay? But that's something we already addressed. We want to form the most stable double bond possible. That's our regiochemistry. So knowing the stability differences of our alkenes, which we talked about in our past units, helps us to be able to answer this question. Okay? Benefits. Okay? The benefits isn't a benefit, it's more a complication. Okay? We have this word rearrangement pop up. Why are rearrangements possible?
Resonance. Reactions.
Why is resonance possible? Resonance gets a bit of a questionable statement. Rearrangements are a direct repercussion of carbocations.
Mm-hmm.
You have a carbocation, you get rearrangements. Okay, they go
Because of
hand in hand.
Resonance.
It's not resonance. Okay, they're both R words, but you're literally moving an atom.
Oh.
In resonance, you cannot move atoms. In rearrangements, you're moving atoms. Okay, so they're similar in effect or appearance. Okay, but they are very, very different in what they are chemically doing. Okay, and then the other really big complication is it directly competes with SN1. The very first step in both the E1 and the SN1 is the exact same. What mechanistic step was that?
The leaving group breaks off?
True, the leaving group breaking off. What's the name of that mechanistic step? So a harder question. I like that you know the leaving group is blanking off. That's good.
I don't know.
Heterolysis.
Oh, yes.
So our cutting, the lysis. And if you're trying to think about future classes, and I don't have to worry about it, biochem is going to throw enzyme names at you, and you have to know what those enzymes do. Breaking down some of their language of what the name means can help. Okay, you get lysozyme or lysis enzymes. What are they doing? They're cutting things. What is heterolysis doing? You're breaking that bond. Okay, so understanding those roots can help you understand what's happening within those chemical reactions. If we push to E2, right, E2 is a reaction up at the top, gets significantly shorter, because in E2, what's happening? We need the leaving group to leave, but we need the leaving group to leave at the exact same instant the pi bond forms. But how does the pi bond form? Where do we get the electrons to form the pi bond? That's right. We get it from the hydrogen located at the beta position. You mean all of the same content applies? Yeah, everything still applies. So you remove a hydrogen from the beta position, the base comes in, removes it, we form the pi bond, there goes our leaving group, all at once. Okay? What's the key word we need to remember for this one? Okay? We can again go back to the steps. Okay? And if you remember them, by all means go ahead and stick with it. But consider in the heat of an exam, you're going to get confused very quickly. And when you say E2, how many steps are you going to think you're going to remember? E2 means? It's not 2 steps, it's 1 step. That's the problem. Okay? The numbers conflict. They're opposite of each other. So you're absolutely right, 1 step. Okay? But that's not a useful or easy thing to memorize because you're bringing in another number and that number directly conflicts with the name of the mechanism. Right? So I caution against that. If you remember it, by all means, stick with it, and I hope it doesn't become a problem. That too should really mean backside attack.
Oh. What about 2 things happening at the same time, or is that just SN?
It's still 2 things. I would argue here it's 3 things-ish. You're forming a pi bond, breaking the hydrogen, breaking the leaving group. So you could kind of run into issues with that. Okay. But I would argue that too means, just like it did for SN2, backside attack. And we'll see why that's important here in a second, and why the way this is drawn is actually problematic. Okay? We still have a substrate, we still have the leaving group, we still have the base, we still have the solvent. So all of those things, and we still form a pi bond. So when we go through and look at our substrate, okay, it's still an elimination, we're still going up in energy, so we want the most stable pi bond possible. And the most stable pi bond is going to come directly from a more substituted substrate. So tertiary is going to be better than secondary and better than primary. This does set up a bit of a dilemma because I can't differentiate E1 from E2 based off of the substrate. They have the same connections, okay? The same ranking system based off of substrates. Leaving groups, I still need a good leaving group. Okay? There isn't much I can do about that. And we could try and push through to all those leaving groups. We'll bring it back here in a second. But largely we're going to ignore it for the moment. Okay? And we'll go to base. Now, is the base important? Okay? The base is important, and we can use backside attack to help us out with this. Okay? Backside attack means that base has to come in and remove the hydrogen from the backside. That base needs to be as strong as humanly possible so that it can get to that hydrogen and rip it off the structure. Okay? So we're looking for strong bases. How do I know it's strong? Okay, and we could start to go through the ranking systems. Size is going to become misleading, okay, or it depends how you use size. Okay? So how are you using size? Is big a good strong base or is it a bad base? What must the base do? And still, we're going back to those definitions because understanding those definitions allows you to apply to a new system. What does the base do? There's two answers. There's the easy answer and the hard answer. Accept proton. Okay, since you gave me the easy answer, that's fair. I'll give you the hard answer. It accepts protons by donating electrons. Right? So if it's going to donate electrons, it has to be willing to share them. If we're looking at a big atom, those electrons that are reactive are being scattered across a large area. How easy is it going to be to react with those electrons? Not easy, which means size, bigger size, is a problem for strong bases. Which is why iodide, bromide, and chloride are all horrible bases. Because they're very large. Okay? Which is going to sound kind of counterintuitive because we could bring in typically a red flag for strong is that it's negatively charged. It's negatively charged and not big. Okay. Going to run into a weird one. What about electronegativity? Should it be very electronegative? That's a hard one. Wait, well, hydroxide is a good strong base, right? Yes, it is. It absolutely is a good strong base. Okay. Does that mean it is the strongest? It's very electronegative. If it's electronegative, what is it doing to its electrons? Careful. It's holding the electrons it has. And if it's holding the electrons it has, can it act as a base? No. Interesting. You say, but hydroxide's a strong base. It is, because it's small. That doesn't mean it's the strongest. What if I look at a negative nitrogen? Both charged, both have the same size, but what's the electronegativity? Nitrogen is less electronegative than oxygen, which means nitrogen is more willing to share the electrons, making nitrogen stronger than oxygen. So we actually want low electronegativity. Last one I'll throw at you for this one. Carbon's probably the lowest electronegativity that we look at, right? So is this a good strong base? What must the base do? Accept protons by donating electrons. And when we talked about our base's ability to donate electrons, what do we need to see? Available electrons. What are available electrons? Lone pairs or pi bonds. Does this molecule have a lone pair or a pi bond? No. It can't act as a base. So just because you have low electronegativity does not mean you act as a base. You also have to satisfy the core definition of what a base must be. Does that make sense? Solvent. Yeah, solvent. The solvent for your E2s are insanely misleading. Okay? They're almost always polar protic, and that has to do with the base. Because the base that we add is almost always some negative oxygen. Okay? And because it's organic, we almost always throw on some organic chain. So we could say something like ethoxide. But the only way we get ethoxide as if I dissolve it in ethanol, and ethanol is polar protic. So your solvents for your E2s almost always invariably come out as polar protic, and that becomes a problem and misleading, which is why I would argue you should ignore the solvent effect when we look at E2 eliminations. But now we move to the really challenging question, okay, which is kind of tied together, our regiochemistry and our complication. Okay, we are still forming a pi bond, so we still want to form the most substituted and stable pi bond possible. But we have to be aware that our reaction runs according to backside attack. If we look at this drawing up here, it's very misleading, so I'm going to redraw it. Here's our leaving group. We got a hydrogen there, we have a CH3 here. Okay, we have this carbon here, wedged hydrogen, dashed hydrogen, we have another CH3 out here. When that leaving group leaves, the base has to come in and remove a hydrogen that is on the back side of the leaving group, okay? And that's where people will go, oh, it's referring to that hydrogen. It can't refer to that hydrogen because those orbitals are in perpendicular, they aren't technically perpendicular, but not in alignment with each other to allow for the formation of a pi bond. Okay? So that hydrogen being at the alpha position is off the table and not relevant. So where we would need to look would be the beta position. Technically there's a beta down below also. Okay, but I wanted to simplify it. And we have two hydrogens there. Are both of those hydrogens equally likely to be eliminated?
No.
No. Which one is the one that will get eliminated?
The one that's pointing away.
Side attack. The red hydrogen, the one that's pointed away, is the one that gets eliminated. The leaving group is wedged coming at us. The backside is dashed going away. The only hydrogen that can get removed is that red hydrogen. The base has to come in from the backside to remove the hydrogen. Why does the base have to come in from the backside? Well, what's the leaving group leaving with? Electrons. What's the base bringing in? Electrons, which is why the base has to be as far away from the leaving group as possible, which is why it's removing the hydrogen on the back side. Okay? This alignment doesn't really fit with backside attack, okay, in the grand scheme of how we would think about backside attack. Okay? So they invented a new word for us. It's known as anti-periplanar. And if you're like, I don't want to memorize that, that's fine. Memorize backside attack. It does the exact same thing as long as we understand what we're referencing when we look at those pieces. Okay? So if we did this, and it's now all happening at once, what product do I get out of this? Take a look at the CH3s. Where are they aimed?
Straight down.
Straight down. Because this all happened at once, can I do a sigma bond rotation? If it all happens at once, can you rotate? No, it's all happening at once, which means there's the new pi bond. CH3s are on the same side. And I would get the cis product. Is the cis product the most stable? No. So we might be like, well, dang, we don't get the most stable double bond. This is part of the complication of our E2 reaction. We have to be real careful to evaluate what hydrogen we're removing and what does that mean for the end product. Before the reaction happens, though, can I do a sigma bond rotation? The answer would be yes. Yes, I can. And when I do this rotation, my hydrogens are now going to rotate down here, right? The purple hydrogen was wedged in my initial drawing. If I do the rotation, what happens to it? It points back. Purple hydrogen here, which means the red hydrogen points at us. When I now go through to do the elimination, which hydrogen do I remove?
The purple one.
I remove the purple one. The leaving group is wedged. I need to remove the backside hydrogen, which is the dashed one, which is the purple one. What product do I get? CH3s are now aimed
Opposite.
trans. A very subtle rotation in the overall structure massively changes the output of our answer. So we have to be really, really careful when we're running an E2 to ensure that we know what hydrogen we're removing to be able to predict the proper stereochemistry of the product. This is a really big complication for the E2 reaction. In this particular scenario, I had two hydrogens to choose from. Which hydrogen was most likely to be removed, the purple or the red?
In the first one?
Not in the first one, because if we look back at this, we'll star the structure. This starred structure and this starred structure have what relationship? It's got two answers.
It's
They aren't stereoisomers.
They're in that tree.
Okay? So one thing we can do is say, well, what's my name?
They're the same.
Hi. What's my name now?
And Mike.
Still Mike. I just did a rotation though. I just rotated my neck. Did that change the identity of me?
No.
No. If it went all the way around, maybe that would probably cease to exist. Right? All we did was a bond rotation. We didn't change any of the connectivity. We didn't change anything else. Those two structures are identical.
Oh.
Okay? Therein lies one of our problems with the E2. If they are identical, which product do I get? The trans or the cis?
Both?
I will get a mixture of both. Should I expect a higher concentration of one than the other?
Yes, trans.
I should expect the trans. Why? As we just addressed with the E1, trans is more stable than cis.
Oh.
The conformational rotation that we're talking about, technically these are conformers of each other. If you go through and look at, heaven forbid, the Newman projections of these, what we'll find is the trans product generates a more stable Newman drawing than the cis conformation, which means in our elimination cycle, the population of our molecule is going to closer match our trans system than the cis. We would expect a larger percentage of the trans product than the cis. What if I only have one hydrogen to eliminate? Can I get two products?
No.
No, because there's only one hydrogen to eliminate. The product that I'm going to get is the proper orientation of when that hydrogen was backside attack to the leaving group. That's the only product I get. Which means we have to be real careful with what? So what would be a giant tip-off that we need to freak out about a question on an exam that we would have to evaluate all of this? It's two big pieces of information. There's an easy answer and a hard answer. Okay, easy answer. If you suspect it's an E2 elimination, you got to worry about this. Not always, because there's another piece of information that has to show up. What's the other piece of information that has to show up to make you go, dang, I've got to worry about this?
2 hydrogens.
2 hydrogens, we actually effectively said we didn't have to worry about it because we get trans. When did we discover this was a problem? Did we discover it with our initial drawing?
With the rotation.
Getting at the right idea. What was added to our drawing that made it relevant to see the difference between our purple and red hydrogens?
The dashes and the wedges.
Wedges and dashes. If you go through and look at a answer or a structure, question stem, where you suspect it's E2 and you see wedges and dashes, all shit's hit the fan, you're dealing with this. You've got to make sure that when you run the elimination, you're in that backside attack orientation. And if it is not drawn in that backside attack orientation, what must you do?
Rotate it.
You have to rotate the structure so that the hydrogen in the leaving group is on the backside. You have to do those manipulations that you were asked to practice and learn in Unit 1. The information stacks. Okay. Oops. Oh crap. That button doesn't work. When we look at our summary. Whoops. Come back here. Okay. Our regiochemistry is dictated by the alignment of the leaving group and our hydrogen. There's that fancy word, antiperiplanar. If you remember it as backside attack, that's fine. That'll help you out. Okay. We do favor the Zaitsev product. We want to make the most stable double bond given a choice. If we are not given a choice, we have to fall back on this antiperiplanar and the alignment comes out as it comes out. There is this word Hoffman elimination. Ignore it. Don't stress about it. Okay, you got enough other stuff to worry about. We don't need to add an exception to it. Okay, so where does that leave us? Well, that leaves us with, we have now covered all of the content, and it's now a question of just applying that content again and again to new reactions so that you're ready for the exam. Okay, we've got a couple summaries. We've got the E1 and E2 mechanism. If you're trying to decide between which pathway you've got for your substrate, E2 says stable product. Okay, just the more I've worked through things. For our substrate, we want backside attack is kind of the thing that I would worry about. Okay, for E1, I want carbocation stability. So the things that dictate that. The things that dictate that, we're going to show up in our substrate pattern, tertiary, secondary, primary, tertiary, secondary. Right? I have the zeroary on there, that's a typo. Zeroary can't run in elimination. They need good leaving groups, so we can ignore that. Our base for the E2, because it's all happening at once, I want a strong base to force that leaving group off, to force that hydrogen to share the electrons across to kick out the leaving group. Okay? The E1, I don't care about the base, okay, which is why it says in smaller font weak base, because it's kind of an irrelevant system. As long as there's anything remotely basic, it'll be fine. Okay? The solvent, misleading for the E2. Polar protic is ideal for the E1. Since it's misleading for the E2, it becomes really challenging to ask solvent questions about E1 because we're ignoring the E2. Okay, stereochemistry. Okay, the anti-orientation, this is talking about our backside attack again. Trans is most likely for our E1. We get cis or trans for E2. That's dependent on our hydrogens that are getting eliminated in that system. Zaitsev's product is going to be predominant all the way through as far as you're concerned, and you can ignore the Hoffman. Okay, So a real quick whirlwind of everything that we just addressed within the last hour. Right? If we push this a step further, what we should see, I believe, okay, is this table, which is something that a textbook that I like that goes into a whole lot more information than you need, effectively takes those same things that we just listed out right here and puts it into a table and then says, okay, if you're going to try and decide how your reaction is going to work, look at those factors and decide what your reaction is. Then you can go through, check off whether it's satisfied, and whichever one had the most check marks wins. Okay? What is strength in reference to? Yeah, see, that's a problem with this table. You don't really know what that's talking about. You jump to it, okay? Base or nucleophile. Okay? Concentration is one that we've kind of dodged and left off the kind of map. Okay? Leaving group ability. This is one of the reasons why leaving group is dumb, because if you have a leaving group, all mechanisms are valid. And if all mechanisms are going to be valid, why even have it as a category to differentiate? Because it's not going to allow you to differentiate. Okay? And then you can look at your solvent effects and kind of populate that out. Okay? I love how you guys are all copying that down, but I just pointed out that it has massive loopholes, right? It would be nice if we had a better table, okay, that matches how we've been structuring and talking about all the component pieces within our reactions. Nucleophiles, strong base, or nucleophiles are bases, leaving group ability, again in small font, substrate, okay, solvent, heat. What you're going through and doing is evaluating what you're given as a reaction. So I can look up at this reaction and be like, okay, what do I have? Okay, I've got Br minus. Okay, Br minus, well dang, it's negative. Since it's negative, that's strong. Okay? It's Br minus. Br minus doesn't act as a base, so it's not going to be a base, it's only going to act as a nucleophile. Which mechanism prefers a strong nucleophile? SN2, check mark in the SN2 box. Okay. Exam prep. I just asked an exam question. What can Br minus act as? Okay. Not only that, we asked another layer behind it. Was it strong or weak? Okay. Those are questions that you have to be able to address. Strong base. It's not a strong base. Since it's not a strong base, it doesn't apply to the SN reactions because they care about nucleophiles. And since it's not a strong base, I'm not going to check off E1 or E2 because it doesn't fit the base category. Leaving group. Do I have a leaving group? Yeah. So I could go through and put in a bunch of checks, but that's not going to be particularly useful. That's why the leaving group is small. Substrate. So now I look at my substrate. What substrate do I have? So being able to quickly classify it. What is the classifications we've dropped on our substrates? Tertiary, secondary, primary. I look at where the leaving group is located, and I want to evaluate how that carbon is substituted. Well, it's connected to two carbons. So I would call that secondary. Because I know what's important for my substrates, does SN1 work for secondary? Yes. Does it work for SN2? Yes. Does it work for E1? Yes. Does it work for E2? Yes. The secondary substrate is the worst substrate to see on your exam because it works for all of them. Okay? Solvent. Where's the solvent? Typically written underneath the arrow DMSO. If it's written as DMSO, are you expected to know what the structure of DMSO is? Okay. First, Lindsay, are you expected to know? No, you're not expected to know. Okay, so if it shows up theoretically, you would see on your exam for DMSO, you would see the structure. If you don't see the structure, that just means it was a typo on my part and I missed it. Ask, I'll draw the structure up on the board. Okay? So you don't have to memorize it. Good job, Annie. Okay? But with the structure in hand, are you responsible for being able to label that as protic, polar A, protic, or nonpolar? Yes. So what is it? It's polar A, protic. Which mechanism prefers polar A, protic? SN2. Put a check mark. Okay? Heat. Heat is typically a red flag for elimination reactions. Do we see any heat associated with this reaction? No. So there's nothing to check off. I could then go through and look at my totals. I've got 2, 4, 2, and 2. What mechanism do I think I'm going to run? SN2. And if I run an SN2 reaction, what would I expect my product to look like then? I would expect the substitution where the bromine goes. So substitution, S, helps us with that. The bromine has to substitute for the chlorine. Okay? But you notice that there was a wedge on the starting material, which means the question is probably also asking about the complication associated with that mechanism, which is backside attack. What's the backside of the chlorine wedged bond? What'd you say?
Is that hydrogen?
I see what you're trying to say. The backside of that chlorine wedged bond is a dash. So the bromine needs to be dashed. That's my answer. What other answer choices could show up on the exam? Yeah, wedged bromine. Every single one of those answers is a legitimate answer. This is why you have to know what mechanism you're running, because it allows you to select the proper path. Okay? And it could be made worse. This could be a multiple select. Choose all of the correct answers, which is really going to be a catch-all for what two mechanisms? Half right. E1 and SN1, because they both form carbocation intermediates. So you could then be set in a system where you would now have to select two answers. And that's because you recognize the parallels between them. Kind of, sort of?
Question probably stupid, but say the chlorine was wedged, or dashed, is it always gonna be that same because it's a backside, so it's just gonna be the opposite?
Yes.
Or if it was dashed, would you then attack? It would still be backside, right?
Is this a valid answer?
No. No, because it's on the wrong carbon.
It's the same, right?
Oh, it's this.
It's the same flipping structure, just flipped over. So this is where we have to be careful. Remember, there is no up, down, left, or right. We can do a quick manipulation of the structure and go, oh, I remembered it has to change to dashed. True, are we drawing it in a way where you would see that it has changed to dash? Or have we also flipped the structure to hide that chemistry? Because are you responsible for being able to do that?
Yeah.
Yeah, that was all Unit 1. That was the whole point of Unit 1. Do you recognize how these structures could spin, flip, or rotate in space? Yes. So, to your question, yes, it is always the opposite, but it doesn't have to look like it's the opposite, if that makes sense.
Yeah.
Okay. I would argue this isn't content, but these are just other summaries that do the same kind of thing. So strength determines your order. So if you have a strong nucleophile or a strong base, that's number 2. So that's E2 or SN2. Okay. Substrate structures. We've got the substrate structures kind of summarized out here. Okay? The one that's really helpful is a primary halide. You're almost always stuck in that SN2 box. Okay? Secondary halide, you're stuck. Hope Rule 1 helps you out. Okay? Tertiary halide, you get a mixture of all three products, but no SN2. So something's now excluded from that system. Okay? Your solvent product typically favors SN1, A product SN2, and then high temperatures tend to be a red flag for elimination. Okay? So this is just trying to target out those kind of big picture things that you could go through and populate that diagram with. Okay? The last piece I'll give you, I do give you this diagram. It's on the very first page of the exam.
And all the other slides too?
No. I don't think you would want that, believe it or not. There's just too much information and you wouldn't have enough time to be able to process anything. So this is, you'll get this table on the exam. So if you spend some time to be like SN1 bad, SN2 good, E1 bad, E2 bad, when you get to the exam, you could then write that out very quickly into your table. And now you can go through every question, and when you see a nucleophile, if it's strong, you can say, oh, that's SN2. Does that make sense? So you could put into those boxes the things that are particularly relevant for you to navigate which mechanism as well. It's just providing you that organizational structure. You don't need it, but it can be helpful. Kind of, sort of? Okay. Just a heads up in case you missed it, our next meeting is the exam.